In this video, we're going to talk about a very, very important pillar of physics, and it's called equations of motion. Even Einstein's equations, the ones that you hear about, the rumors that they are so difficult to understand and things like that, at their core, at their heart, is these equations of motion that we are going to discuss. He took them to a more advanced level, but at their core, they came from these considerations, these equations. A very important concept is something called uniform acceleration. These equations of motion only apply when we have uniform acceleration. But what is uniform acceleration? From what you remember, acceleration is the change in velocity per unit time, right? So let's say 1 second, I have a velocity of 20 meters per second. And then after 2 seconds, let's say I now have a velocity of 40 meters per second. And after 3 seconds, I have a velocity of 60 meters per second. After 4 seconds, I have a velocity of 80 meters per second, right? Let's compare it to a situation where in 1 second, I have a velocity of 20 meters per second. In 2 seconds, I have a velocity of 30 meters per second. In 3 seconds, I have a velocity of 60 meters per second. And in 4 seconds, I have a velocity of 120 meters per second. These are just scenarios, like random scenarios, random numbers. I don't know if this is even physically possible or not. I have no idea. But I want to talk about something called uniform acceleration. Can you see the acceleration? We said acceleration is a change in velocity, right? These are velocities. We are looking at the speedometer and trying to see what is the velocity. It's 20, it's now 40, it's 60, it's 80. And another person is looking at this, another speedometer is saying mine is 20, 30, 60, 120. Acceleration, we say, okay, how did you accelerate in the 4 seconds? This one will say, in the first second, I accelerated by 20 meters per second. Because acceleration is the change in velocity, right? What was the change in velocity here? 20 meters per second. What was the change in velocity in the other second? 20 meters per second. The change in velocity here, 20 meters per second. Good. And then this person will come and say, my change in velocity in the first different second here, my change in velocity was actually 10 meters per second. And then my next change in velocity was 30 meters per second. And then my last one, my change in velocity was 60 meters per second. I think you can already tell which person here, between the two of them, moved with uniform acceleration. I hope we can all agree that this person here is the one that moved with uniform acceleration, because his velocity changed by equal amounts every single time. It was equal amounts. It's like when I was talking in the previous videos, like, Gogos and the robots, they take it so slowly, increasing their velocity by equal amounts in equal times. So when we change the acceleration, when we change the time by 1 second, their velocity increased by 20. When we change the time again by 1 second, their velocity increased by 20, which was constant. But this person, when they changed their time by 1 second, their velocity increased by 10. When we changed the time by 1 second again, their velocity changed by 30. 30 is not equal to 10. You see? So this is not uniform acceleration. And equations of motion will not apply in this case. They will apply very well in this case. In this case, equations of motion will apply very well because it's uniform acceleration. So let's get into what equations of motion are. What are they? You see? So we're going to first start with an object. We're going to look at an object moving in a straight line. That is another thing to emphasize. Behind uniform acceleration is motion in a straight line. The reason for that is acceleration, like I tried to emphasize in the acceleration video, is composed of magnitude and direction. If the direction is changing, then we do not have uniform acceleration, because it means acceleration is changing. It is changing acceleration because of no constant direction. So these equations of motion, they apply mostly with motion in a straight line, if I'm not mistaken. We'll see as we go with examples, but if I am wrong, I'll correct it later. But for now, let's see this motion in a straight line. Object moving in a straight line. So we're looking at an object moving in a straight line with uniform acceleration. There, the word comes, with uniform acceleration. It has to be emphasized. It's moving with an uniform acceleration a, so the acceleration itself is a. Its velocity increases from u to v in time t. So velocity has increased from a value u to a value v in time t, right? Now, from definition of acceleration, this is definition of acceleration. We know that from definition of acceleration, our a is given by change in velocity over change in time. Remember, change in velocity over change in time. Straightforward stuff, right? So this is equal to, but what is the change in velocity over, what is the change in velocity? My change in velocity, let me just write it in symbols. My change in velocity is just going to be the final velocity minus the initial velocity. We said the velocity increased from u to v. So this is the final velocity v. So it's going to be final minus where it started from, which is u. When you subtract the two, we have calculated the change. That's how you calculate change, right? Divided by time, which is a change in time, which is going to be our t. Therefore, my a is equal to v minus u over t. I think we agree with this one. And this gives us our first equation of motion. If we make the final velocity v the subject of the formula, we come up with v is equal to u plus a plus at. U plus at, and that is equal to, this is equal to our equation number 1, equation of motion number 1. Basically says final velocity v is equal to initial velocity plus acceleration times the time taken. This is, you can read the statement. The object started at velocity u, accelerated at a in time t. So this at is just the addition of the velocity. When it was acceleration per second, a means how much velocity were you adding per second. So if per second we're adding a, in the total time t, how much, what is this at calculates the total velocity that was added onto a to get our final velocity. Straightforward like that. So that is our first equation of motion. Then, now we are going to suppose an object. We're going to look at an object. Let me take this up a bit. Yeah, so I don't know. Okay, cool. So we're going to look at an object with velocity, u. Let's say it accelerates with, again, what type of acceleration should we consider? Uniform acceleration. So an object with velocity u accelerates with uniform acceleration a in time t, attaining velocity. So after acceleration, it attains this velocity v. Therefore, distance traveled. Let's look at distance traveled. We know distance traveled is equal to velocity times time, or speed times time. There is a special definition of velocity of distance called S is equal to average velocity times time. We're just saying in that period where it was moving with some velocity, changing its velocity, we are going to take an average of that velocity and just multiply it by time. Right? We're just going to take the average. what is the average velocity that it moved in that distance or in that time, and then multiply it by time. It's sort of like speed times time, or velocity times time, just that we're taking an average, or the number that is in between u and v. That is between u and v, just the average of those two, and multiply by time. How do you calculate the average? It's just going to be u plus v divided by 2. So half of u plus v, that is my average velocity, right? Times time. Straight like that, isn't it? But what did we see with our first equation? But our first equation said v, this first equation, it said v is equal to u plus at. So which means we can replace this v by this calculation on the right hand side, because that side on the right hand side there, this one, it is equal to v. So this becomes s is equal to half of u plus at, when we have replaced this v by u plus at, times time. Cleaning that up a bit, it becomes half of 2u plus at times t. Putting the t inside, it becomes equal to half of 2ut plus at squared. That's my s, right? And then putting the half inside, this is now straight algebra for maths. Our s is now equal to ut plus half at squared. Straight up algebra. And by that we've derived the second equation of motion, number 2. And this, I think we've seen it before when I was talking about objects falling and stuff like that, parabola. This is how you derive it. And it makes sense. The distance traveled is just going to be ut plus half at squared. Ut is just the distance that you traveled initially plus half of at squared. A being my acceleration times the time squared. Easy stuff, I think. That's the second equation of motion. Now, let's be mathematicians for a bit. From 1, v is equal to u plus at. Therefore, my t is equal to v minus u over a. Agreed, right? I just made my t the subject of the formula here. What if we replace this t in our second equation of motion by what we have calculated here? So, wherever there is a t in our second equation of motion, let's put v minus u over a. What do we get? S is equal to u, v minus u over a, plus 1/2 a v minus u over a squared, right? Let's see where that gets us. Therefore, my s is equal to, let me rewrite it nicely as this, u factor of v minus u over a plus half a factor of, no, wait, let me not write it like that. Let me write it as v minus u squared over a squared, because these two factors, v minus u over a, this factor v minus u over a is being squared, so it means it's v minus u squared over a squared. So I'm going to write it like that. So now what's going to happen is this a is going to cancel 1a here, right? It's going to cancel 1a, and so it becomes u factor of v minus u over a plus v minus u squared over 2a. That's what it becomes, right? And so my s is equal to this thing on the right hand side. But that thing is nasty. We have a and 2a in the denominator. We don't want that denominator. Let's get rid of those denominators, right? We multiply everything by 2a. The common denominator. Common denominator is 2a, so we multiply everything by 2a. Since we did it on the right hand side, we are going to do it on the left hand side. So my 2as is just going to be equal to, this a cancels this a, so it becomes 2u v minus u plus this 2a cancels this 2a, it now becomes v minus u squared. Agreed, right? You can do a method that works for you. Yeah, just multiply throughout by the common denominator to get rid of the denominators on the right hand side. We're running out of space, but I hope it'll be enough. Therefore, let's clean this up a bit, removing the brackets. So 2as is going to be equal to 2uv minus 2u squared plus v squared minus 2uv plus u squared. Is it plus u squared? Yep, it's going to be, I think it's going to be something like that, right? It looks like that. Let's see. Now, like terms subtract each other, they neutralize each other and stuff like that. Let's apply that. 2as is going to be equal to this 2uv is going to subtract 2uv and they neutralize each other. 2uv minus 2uv is equal to 0. They neutralize each other. Minus 2u squared plus u squared is going to give me minus u squared, right? Plus v squared. This is just going to be plus v squared. Cleaning this up a bit for it to look nice, we get v squared is equal to u squared plus 2as. And that is our third equation of motion. This becomes our third equation of motion, which just says final velocity squared is equal to initial velocity squared plus 2 times acceleration times the distance the object covered, or distance object covered or distance traveled by the object. So as a recap, this is our first equation of motion, and our v represents final velocity. V is always final velocity. Our u is usually always initial velocity. That's just by convention. I don't know how v or u, they don't even sound like final, or you would have thought maybe f and I, but that's just the convention. V is final velocity and u is initial velocity. V is equal to u plus at. In our second equation, the new term that we have introduced is s, which is our distance traveled. It's going to be distance traveled. Here we do not exactly look at displacement because we have said this object is moving in a straight line. I think we're considering objects that are moving in a straight line. So in a straight line, it's like we know where this object is going. So we're just going to talk about distance traveled in that direction of the straight line. So we know that this distance is going to be distance in that straight line facing that direction, whatever it is, right? So s is equal to ut plus half at squared. And our u being our initial velocity, our t being our time, obviously, and our a being our acceleration. And then the third one, v squared, we said this is final velocity, u squared being our initial velocity, and then our a, acceleration, our s, the distance that the object traveled. These are our 3 equations of motion. In the next video, we're going to apply them to a couple of examples.
Created with free version for non-commercial use.